Okay, I'm in the scratch space. All right, this is where I develop problems for future problem sets. There's no real solution to the equation 10 to the x equals log base 10 of x, but if you shift either curve a units horizontally, the two graphs will eventually meet, initially at one point, but then at 2 points. Ideally, we'd like to know when these two graphs meet at a unique point. Use Newton method to find this point. All right, so what I'm going to do is go to the whiteboard, and what I'm going to do is just kind of visualize the problem first off. All right, now certainly a lot of times when you're visualizing the thing, it's not the best picture, but I'm not looking for a picture that I'm going to answer the question from it. But what I'm going to do is there's this log function, looks like this over here. Then there's this exponential function, looks like this over here. And what I'm going to do is I want to move this thing to that thing so it just touches it. All right. Now, how would you do that? Well, this curve over here is y equals, that's going to be log base 10x. And this curve over here is y equals 10 to the x. Well, one of two things I could do is I could either move the log function or the exponential. I'm going to move the exponential a units to the right. And a is a positive number. So the way I do that is going to write down 10 to the x minus a. It's a standard translation, equals log base 10x. All right? Now, I want to visualize that for you. Let me get my eraser out, the big eraser, get rid of this. Again, I want to emphasize over here that a is a positive number. Put my graph down like this over here. And if I were to graph this guy out over here, where a is a positive number, by the way, that's going to be shifted. All right, I'm going to say it's shifted over here somewhere, like this. And then the other guy, this guy over here, what do I have? Let me draw that picture. It looks sort of like this over. Let me go back to black. Looks like this over here. Again, not the best thing. But they're going to intersect somewhere. And I want it to intersect at a unique point, not at two different points, just one point. That's going to be a point of tangency. Now, since it's a point of tangency, what I want to do is take its derivative. All right? So let me think about that. And the derivative, I'm going to remind myself, right? So if I have a exponential problem, like y equals, I'm not going to use the letter a, use b to the x. I probably would take the log of both sides. I'll do natural log, because natural logs are easier to differentiate. It's going to be x ln b. Then take the derivative of this, it's 1 over y dy dx equals ln b. So what do you get? Dy dx would equal y, which is b to the x times ln b. So I'm ready to take the derivative of the left-hand side. And what I want their slopes at that given point will be the same. So I'm looking at the derivative of each of those functions. So let's do this first one. The base is 10. So it's going to be 10 to the x minus a. And then I'm going to get the natural log of b, the base, which is 10. Okay? Let me get my eraser out. I just did the derivative there. I'm going to erase this now. And I want to take the derivative the other side. All right? I can write that down. And again, since I can't remember things, I'll write them down. So log base 10, x. I'm going to say 10 to the y. And that's going to be x. Just rewriting it. Take the log of both sides. You get y ln 10 ln x. And let's write this down. So dy dx ln 10 is going to be 1 over x. So dy dx will equal 1 over x ln 10. All right, write that down. 1 over x ln 10. All right? All right, what are we going to do now? We have two equations and two unknowns, and there's a good chance we'll be able to figure this out. And start to erase things. And what I'm going to do here is I'm going to divide this equation, the second equation, by the first equation. Let's write that down. 10 x minus a ln 10, second equation. And this is going to be 1 over x ln 10. I'm going to divide it by the the first equation. So it's going to be 10 x minus a. Now, let's see, I'm going to divide, right? So I'm dividing by that, that log thing. And what do you get over there? Well, I'm just going to write this way, log base 10 of x. All right, what's nice about this is that this thing disappears now. And what do you get? I'm going to simplify it a little bit. You're going to get x. I'm trying to get rid of the fraction now, or the rational ratio. ln 10, it's going to be squared, log base 10x is equal to 1. I'm sure I did that right. Yeah, I think so. I just multiplied both sides by this thing here. That's all I did. Let's make sure I did that right. X ln 10. Yeah, I did that okay. Now here comes the trouble. And I'll go through it with you, what the trouble is. The trouble is solving this equation. And it's not an easy equation to solve. So what I would recommend over here is to use Newton's method. Which I will go through with you. All right, I'm going to do it in a separate video, but I'll go through that with you. And that video will be linked in the document. And in order to do Newton's method, I need to solve this thing for 0. So one way to do that, you simply subtract 1 from both sides. And you get ln 10 squared log base 10x minus 1 equals 0. And I'm going to call this a function because Newton's method is all about finding roots. All right? Now granted, since I'm going to use Newton's method, I really need to be able to use a computer. And computers are really efficient at doing a lot of different things, including taking derivatives. So what I'm going to do is I'm going to go to Sage, and I'm going to code this. Now what I'm going to code? I'm going to code putting this in. Oops, not the 0. Just this. I'm going to code this. So like in Sage, what I'm going to do, I'm going to say, first I'm going to say reset, and I'll go to Sage and do it for you. Oops, I don't do that. There's no argument to that. And then what I'm going to do is I'm going to define f of x, and in Sage it looks like this over here. F of x equals x star. Now there's something strange about Sage, by the way. The natural log is just log. So I'm going to say log, that's natural log, by the way, 10, put a little square symbol on it. Tell you what I'm doing over here. I'm just doing this thing over here. And that's going to be times. Now, if I want to put log base 10 in, I'm just typing log again, x, but I got to tell it the base is 10, and then minus 1. All right? So this is one line, that's another line. Let's go to the next line. The next line I define Newton's method. I just say nx equals, and nx is going to equal x minus f of x divide by its derivative. And in Sage, it's pretty easy to take a derivative, even complicated things. diff f of x with respect to x. This is my function now. Now, so I can get a guess over here. I'm kind of looking at my picture up here. And, I'm making a wild stab at it. I'm going to say, oh, maybe I moved it over 2 units. Who knows? All right, I don't know. So, again, when I say this, I'm wondering what that x is. And I'm just going to make a wild stab at it. I'll just say, let's make it 2. All right, x equals 2. Maybe I shouldn't say moved it over 2 units. I'm just saying maybe this thing hits around 2. I'm not saying it does. I'm saying maybe it does. But it's some positive number, by the way. So in Sage, the next thing I put down, I'd assign x to be 2.0. Now someone says, why using a decimal? I'm trying to force Sage to do something, make a computation. Then what I do is I type this in. I want another guess, and I say x is going to be assigned now, nx. Now I want to point out what's happening over here. In Sage, what's happening is this thing now is the number 2.0, and 2.0 then gets shoved into this thing over here, which is what the nx function is, and does a computation. But I want to display it. So I use this, and I want the x to be displayed. Unfortunately, the x is going to come out really wacky looking. So I'm going to say over here, approximate it, force it. I'll tell you the number one reason why. Log 10, natural log of 10 is a really nasty looking number, all right? So I need to force Sage to actually write down the nasty looking number. And then I keep hitting the return button, all right, to this one over here. And just keep doing it over and over and over and over again until there's no change. Again, it does take some time, but the computer's doing the computation for me. And you're eventually going to arrive on an x over here. You'll eventually get an x. And the x is going to be approximately 1.372. I'm not going to write it down, but I'll do it in Sage for you so you see what it looks like. Then someone says, is that what you wanted? No, that's not what I wanted. I wanted the a. Now, really what I found out was that the x over here, it wasn't 2 like I thought it was. It was actually 1.37, yada, yada, yada. All right? But I want to get the a. Right? Now, so how do you do that? I got to solve an equation. All right? What equation do I need to solve? I need to solve that equation. Let me remind myself. I got to look back over this over here. Where, let me think about that. The log base 10 of x would be the same as log, not log, 10 to the x minus a. Now I want to point out what's happening over here in Sage when I do this, and I'll go through that in Sage. Sage doesn't see x anymore. It sees this really crazy looking long number that's approximated, and it puts it here, puts it there. And then what I need to solve that. So in Sage, the command is going to be solve. It's going to be solving this equation over here, and I'll type this in for you, by the way. That's an equation you type in, and I need to solve for a. And I'll go through that, and I'll show you when I do that, the a is approximately 2.234, yada, yada, yada. But again, I'll do that in Sage. Here's the take-home message, though. I think for most students, setting it up is the tough part, all right? Now, again, knowing that you're going to move something around, so they intersect, draw a picture first. Then when you do take the derivative, and the derivative took some effort, by the way, and then eventually you get an equation. That's an equation we got. How do you get Newton's method? You have to solve for 0, and then you apply Newton's method to it. And again, hopefully it goes smoothly for you, depending on what your guess is. Again, if you have a computer, I would recommend you use a computer. I would not want to do this by hand, by the way. Thank you for paying attention.